Darkness is faster than light, and researchers were able to prove this in a new study. And in doing so, they have experimentally confirmed a 50-year-old theory. Yet, we've actually known since Einstein's special theory of relativity that nothing can travel faster than light. We spoke with Professor Lindfors from the University of Cologne, where I also studied back in the days, and who conducts research in optics. And he helped us to put the whole thing into perspective. So, why darkness is faster than light, how the research team was able to demonstrate this, and why the special theory of relativity isn't violated after all, you will find out in that video. And with that, welcome to the German Science Guy. I'm Dr. Jakob Beautemps, and in Germany we say, los geht's. Okay, we know from everyday life, in physics, speed can add up. Here's an example. Imagine you're sitting on a train that's racing through the station at 100 km per hour as seen from the platform. Sorry if I stay with kilometers per hour and not make it in miles, but in the end it doesn't matter, it's just an example. So 100 km per hour as seen from the platform. At the same time, another train is passing by in the opposite direction at 70 km per hour as measured from the platform. If you now measure the speed of the passing train from inside your train, you will find that instead of 70 km per hour, it's traveling at 170 km per hour from your perspective, so the speeds add up. That makes sense, doesn't it? But even over 100 years ago, it was shown that this does not apply to light. And ever since the special theory of relativity was published in 1905, we've known that nothing travels faster than light in vacuum. At least until now. Israeli scientists have shown that darkness is faster than light. It sounds absolutely crazy. Of course, we will explain what's behind it, but to understand that we need to take a look at a few basic principles first. Okay, first we need to clarify, what is light anyway and what properties does it have? Well, light is first and foremost electromagnetic radiation. This means that energy is transmitted in the form of electromagnetic waves or photons, that is, particles of light. These electromagnetic waves are nothing more than electromagnetic fields that propagate through space. An important quantity in connection with light is phase. Phase indicates at which point in an oscillation the light waves currently are. For example, where the waves have a through, a crest, and so on. The waves can now simply oscillate perpendicular to the direction of propagation. If we then freeze them, so to speak, and examine the phase in a plane centered at the origin, we see that the phases of all the waves are the same in that plane. This region of equal phases is called a wavefront. But that's not the only way waves can oscillate. Vortices can also occur. We are familiar with air or water vortices from everyday life, for example. If you pull the plug out of the bathtub, the water swirls down the drain. And in fact, light waves can also form vortices. Of course, they don't actually swirl down the drain, rather you pass through every phase as you move in a circular around the central point of the vortex. These are also referred to as optical vortices. They can either be created intentionally using a so-called phase modulator, or they can occur more or less randomly when a large number of light waves scatter and interfere with one another within a material. What is unique about optical vortices is this. At the center, the phase is undefined. In mathematics, this is therefore referred to as a singularity. At the same time, the intensity of the light inside the vortex is zero, or in other words, it is dark. This is comparable to the eye of a hurricane. And this singularity arises because the light waves cancel each other out inside the vortex. When the waves cancel each other out, there can of course be no phase because there is no light. And it is precisely this singularity that is the dark spot that can move faster than light. The researchers have demonstrated this and thereby confirmed a 50-year-old theory that predicted this. And with that, we finally come to the study. Let's first take a look at what they did before we move on to the results. So they generated phonon polarizons. Put simply, these are light waves coupled to a lattice vibration. Lattice vibrations are oscillations in solids. In the case of phonon polarizons, however, these vibrations do not occur independently of the light waves, but are coupled to them. And that's where such optical vortices can occur. To generate the phonon polarizons, the researchers used a boron nitride membrane. This is a material used as a lubricant that resembles graphite. The wave packets generated were comparatively slow, a full 100 times slower than the speed of light. Paradoxically, according to the research group, this is also the reason why the singularities reach superluminal speeds, so faster than light. But more on that later. So they generated left and right-handed vortices here. To capture images of the phonon polaritrons, they then used an ultra-fast transmission electron microscope. Within 855 femtoseconds, they captured 285 images. For comparison, one of the world's fastest film cameras shoots at 5 trillion frames per second. Using the microscope, the researchers captured 333 trillion frames per second. However, these weren't captured all at once. Instead, the researchers sent a light pulse each time, and the camera took a picture 3 femtoseconds after the start, 6 femtoseconds after the next pulse, and so on. The images can then be assembled like a flipbook, which ultimately results in this high frame rate. This allowed them to observe the motion of the singularities. Based on these observations, they were able to determine the position and velocity of the singularities. And the result? On average, the speed of the waves was 1.04 times the speed of light. A full 29% of the singularities reach superluminal speeds. The low speed of the wave packets is also responsible for this. According to the researchers, this statistically ensures that there are many singularities traveling at the superluminal speeds. Professor Lindfors explains this by noting that the low speeds greatly favor the superposition of many wave components within the material, and the optical vortices arise precisely from such superpositions, which in turn favor these speeds. But the question now is, if the special theory of relativity states that nothing can travel faster than light, how are these research results possible? At this point, we need to take a closer look at what the special theory of relativity actually states. The key point is this: neither mass, nor energy, nor information can be transmitted faster than light. But if none of these are being transported, there is no reason to rule out superluminal speeds. And that is precisely the case with singularities. The motion of the singularities is in fact purely geometric depending on time. It is a property of the evolving phase landscape. Put simply, this means the waves in the boron nitride are scattered, reflected, and superimposed within the material. So there is a constant change in this wave landscape. And it is precisely these geometric changes that cause the singularities to travel faster than light. According to Professor Lindfors, you can think of it like a pair of scissors. If you close an extremely large pair of scissors relatively slow, the tips still move at superluminal speeds, but they are just a part of the large pair of scissors, which otherwise close much slower. And that's how it is with singularities as well. They are simply part of the interference patterns and cannot be controlled independently. This all sounds very theoretical right now, but the researchers also point out, using this microscopy technique, we can discover entirely new phenomena in biology, chemistry, and physics. Optical vortices can also be used, for example, as a kind of wrench to capture small particles and steer them along a circular path. Optical vortices could also be used in quantum electronics. But we need to properly contextualize the study's findings and examine them critically. And you know this from every of my videos. As always, we will do this in the big hurdle. Be sure to click subscribe first so you don't miss any more videos. Okay, well, first of all, it goes without saying that what the researchers studied is basic research. So it's actually pretty hard to come up with a real big hurdle. Still, there are a few limitations that they themselves point out in the paper. One limitation is in fact the microscope. It's truly amazing that they were able to study these singularities and superluminal speeds. But the microscope also reaches its limits here. Theoretically, the speed of the singularities could be orders of magnitude higher, but that can't be resolved with the microscope used, or any other in the world. So there's still room for improvement. Last but not least, it's important to note, for now the results apply only to the material studied and could be significantly more complex than other materials. But I think that's a very minor hurdle and actually reflects what might be possible in the future. Ultimately, what I found most fascinating is the technology behind the research. The fact that such incredible resolutions can be achieved is simply thrilling and demonstrates once again what research makes possible. And Professor Lindfors also reiterated at the end, just because we don't know of any applications yet doesn't mean there won't be any in the future. In the past, there have been many examples where applications didn't emerge until much later. take the laser for example. And today it's impossible to imagine life without it. But now I'm curious to hear your thoughts about it. What do you think of these research findings? And did you know that light can swirl? Feel free to share your thoughts in the comments. Otherwise, as always, vielen Dank fürs Zuschauen. Thank you very much for viewing this video. It's always a pleasure. And I say auf Wiedersehen, which means goodbye, your Jacob.